Hello, fellow problem solvers. So today we're going to be doing a problem from the 29 IMO, problem number 2. I suggest you try this problem out for a minimum of half an hour, ideally an hour to an hour and a half, but not more than 2.5 hours. If, on the other hand, you would like to go along with us, I suggest you take 15 minutes to draw the picture and write down your first ideas. What would you do first? So now, let's begin. So the first thing for geometry problems that's important is your diagrams. Draw decently good diagrams that you can work with. And another thing which can be very useful in geometry is to draw the points one at a time. So when we have P and Q, put P and Q down and see if you can get anything from that. Then draw points K, L, M and see what can you infer from that. And only then do you go to the final part of the problem. Now in this case, drawing P and Q, what we can only infer is, given that the problem statement is prove that OP equals OQ, we can ask ourselves, when is OP equal to OQ? Now this is a question you would like to answer if you were to solve the geometry problem backwards. And what I mean when I say solve the geometry problem backwards is really there's two ways you can solve a geometry problem. That doesn't really apply to all Olympiad type problems. But with geometry, you can go from the thing you need to prove and try to work backwards to a fact that you know, or you can go from the facts that you have and try to work your way up to the thing that you need to prove. Now in this case, I ask you to take 5 minutes and try to go backwards. What would hold if OP is equal to OQ? Can we get rid of O somehow? Now the idea here is to use the power of the points P and Q with respect to the circumcircle of ABC. Namely, what we have from the similarities of triangles AP1P and the triangle P2CP, what we would have from that similarity is PP1 over PA is equal to PC over PP2, which in turn implies that PA times PC is equal to PP1 times PP2. Now, if you look at it in terms of the radius and the distance from P to O, what you have is PP1 is equal to OP1 minus OP. And PP2 is equal to OP2 plus OP. Now given this is R, this is X, this is R, this is X, we have this is equal to R squared minus X squared. In other words, it's equal to the radius of the circumcircle squared, which is a constant, OA squared minus OP squared. And now from here, what we have is, namely that PA times PC is equal to OA squared, which is the radius, minus OP squared. And similarly for Q, we'll get that QA times QB is equal to OA squared minus OQ squared. So the condition that OP is equal to OQ is equivalent to PA times PC is equal to QA times QB. So maybe that, and that's a better thing to prove. And the reason for that is that we get rid of a point O, which really doesn't have anything to do with the other points in the problem. Now I invite you to take 10 minutes and draw points K, L, M and see what you can do. So now we drew the points K, L, M. They are the midpoints, first and foremost, of BP, QC, and QP. So let's first infer what we can get from them being the midpoints of these segments. Namely, we have some midlines, namely the midline ML and AP, and we can infer some angles. So let's call this angle X. That means this angle right here is X, and this is gamma minus X. Similarly, this angle is Z. That means this angle is Z. This is beta minus Z. We have this angle right here is equal to this angle right here, and this one right here is equal to this one right here, which means angle PML is APM. And similarly, AQM is equal to QMK. Now let's take a look at what happens when we consider the tangency condition. That is the next condition. So geometry problems are really cute in the sense that they're great in the sense that you can take them one point at a time and you can slowly build up. You write a couple of points which are in the first two sentences, you infer much information about them as you can, and then you move on to the next sentence in the problem. So they're very good like that. Now, let's look at the tangency condition. If QP is tangent to the circumcircle of KLM, then that means that the angle AQP is equal to the angle QMK. This we already have, but this means that the angle QMK is equal to the angle KLM. So this angle right here, call this phi, and then we have that this here is also phi plus x. Now take 5 minutes and see what you can do with this. Well, what you can do is you now infer that AQP is equal to KLM, and similarly APQ is going to be equal to the angle PML is going to be equal, by the tangency condition, to the angle LKM. Now what does this tell us? Well, we have the angles of AQP and MLK are identical, which means there's a similarity condition, namely AQ over ML is equal to AP over MK is equal to PQ over KL. Now, look at the condition. We need to prove that AQ times BQ is AP times BC, which really translates to proving that AQ over AP is equal to PC over QB, right? This is what we need to prove, and this is what we know. So immediately from here, the idea is that let's just look at what we have. We have AQ over AP is equal to ML over MK. Now, can we connect this to this? Take 10 minutes and try to figure it out. Here's the idea. So this is what we have. We have this that we know to be true, and we know that this is enough for us to finish the problem. So what we need to prove is that ML over MK is equal to PC over BQ. Now, why am I optimistic that we will get to this very fast? Well, the reason I'm optimistic is because ML and PC are right next to each other right here. And so is MK and QB. And if we take more than a moment, we will see that ML is actually, because this is the midline of the triangle QPC, that means ML is actually equal to half of BC. And MK, because it's the midline of BQB, is equal to half of BQ, which means that ML over MK is equal to PC over QB. And now from AQ over AP is equal to ML over MK via this similarity, and given that this is equal to half of PC over half of BQ, which is equal to PC over BQ, we can infer that AQ times BQ, when we multiply these together, is equal to AP times PC, which implies that Q and P have the same power of point with respect to the circumcircle of ABC. And this implies that OP is equal to OQ, which is what we needed to prove. Now let's formally write this down. We first say, given the QP is tangent to the circle that goes through points KLM, we have that the angle QMK is equal to MLK and PML is equal to MKL. And then we say, given that MK and ML are the midlines of the triangles QBP and PCQ, we have MK is parallel to QB, ML is parallel to PC, which is parallel or identical to AB, parallel or identical to AC, which implies that the angles QMK is equal to AQP and PML is equal to APQ. And now, given these two, we have from these angles that AQP is similar to MLK, which means that AQ over AP is ML over MK. And given ML and MK are midlines, this means that ML is equal to half of PC and MK is equal to half of QB, and this ratio is equal to PC over QB, which implies that AQ times QB is equal to AP times PC. Now this implies that Q and P have the same power of point with respect to the circumcircle of ABC. And this right here implies that OP is equal to OQ, which is what we needed to prove. And as always, thanks for problem solving.